Okay. Hello, everyone. So, can you hear me in the back? Can you hear? If you can hear me in the back, can you wave or nod or something? Nothing? You can't hear me? You in the red coat, can you hear me? Hello, hello. Okay. So, let's get started. I just had, it's okay? No, weekend is closed. Can you please? So, we're going to start with a little recap of what we did last week, or at the beginning actually of Monday. We had this slide here that was from lecture 4, slide 20, which summarized a little bit our discussion of how to find global and local maxima. And I just had in the office hour, I had a student, I'm sure she's here somewhere, and she asked a really nice question, which made me think that I perhaps want to say the same thing here that may help. So the question was about finding global optima. And we are looking actually in open domains. Okay, we know that finding a stationarity point is a necessary condition to find a global maximum. Okay, let's talk maxima. Okay, so we need a stationarity point, and the question the student had was, well, we now have two sufficient conditions, and they were here, right? Which could help us to find whether an actual point, a stationarity point, or whether a local maximum is actually a global maximum or not. The first sufficient condition involved looking at the derivatives, and the second sufficient condition involved looking at the concavity or convexity property of the function across the whole domain. And so it's important to know these are both sufficient conditions, and they are slightly different. Okay, but if you found one, if you realize that one of these sufficient conditions is met, then that's fine. Then you can decide we have a global maximum. But do remember they are sufficient conditions. So there could be a situation where none of these two sufficient conditions is met, and yet you have a global maximum. Okay, because there are sufficient conditions, not necessary. And let me just illustrate this. So first, I will illustrate a case where this sufficient condition is met, but this one isn't. Okay, there are slightly different conditions, and the second one involving the second derivative is a stricter one. Okay, so I'm going to give you a graphical example of a function where we have a global maximum, and we can tell by this sufficient condition, but not by this one. Okay, so think of a function. We have a stationarity point. Okay, and let's think about this first sufficient condition here. It says that to the left of this point, so in this direction, the first derivative of the function should always be positive. Okay, so let me just draw a function here. Okay, and what does it mean? Always be positive means the function should always be increasing, right? Okay, so that's fine here, right? That function is always increasing. And to the right, the function should always be decreasing because f prime is 0. So let me do it like this. Okay, so this sufficient condition is met here. Well, just assuming nothing strange happens to either end. Okay. What about this sufficient condition? Okay, here we are basically asking, is the second derivative smaller than 0 for all x across the entire domain? And what does smaller than 0 mean? It means it's concave, okay? Or it means that the first derivative should always be decreasing. Is there a part of this function where the first derivative isn't decreasing or where the function is convex? Yes, okay, this part of the function here, right? Here the function is convex. Actually, so as we go, I brought a ruler here, let's see whether that works better. So if we are here, that's the derivative, we are decreasing, 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 but now we're actually increasing the first derivative. So we are having a convex part of the function, okay, and then we are decreasing again. So that second sufficient condition is not met, but the first one is, okay, and hence we have a global maximum. Let me now give you an example where neither of these two sufficient conditions is met, but yet we have a global maximum. Okay, let's say we again have like a point here, okay, and this is a local maximum, and let's say that function looks like this. And let's make it fairly straightforward here. Okay, so let's see. So we now have actually several stationarity points, right? Here we have 3 stationarity points. We immediately see that this one is in a convex part of the function, so the second derivative here is larger than 0, so that's certainly not a max. It's not even a local maximum, but we have 2 local maxima. Could one of them be a global maximum? Well, you see, it's perhaps immediately obvious, but perhaps not. That let's look at this point here, this particular one. To the left of this function, the first derivative is always positive. The function is always increasing. Okay, so that part we have a tick. But this part here, to the right of that point, the first derivative is not always negative. It's negative, negative, but then it's positive again here, the first derivative, negative again. Okay, so this sufficient condition isn't met. Let's see that one here. We want the second derivative always to be smaller than 0, so we want the function to be concave everywhere. That's clearly not met either, because again we have a convex part of this function here. Okay, so again the sufficient condition isn't met. But still this could be a global maximum. Okay, it depends what this function does here. Okay, let's say that function just goes further down. So how would you figure out whether this is a global maximum? You can't use any of these 2 conditions up there. So all you're left with here is you check, you compare, you have several candidates because you have several local maxima. So how do you know which one of these is better? You plug in the function value and see which one gives you a higher, or you plug in the argument and see which one gives you a higher function value. Easy. Okay. But perhaps you also need to check what happens to the function at the extremes. Because this, how I drew this function, that seems to be quite benign. Perhaps that goes further down always. Okay? But what if the function here on the right looks more like the red one? Okay? Then we would have another stationarity point. Clearly this is a local minimum, we wouldn't consider this. But here the function as x goes to infinity goes up, perhaps to infinity, but perhaps all that's important, does it go to a value higher than this one? Okay? So if you can't use your sufficient conditions to establish whether you have a global maximum, that does not mean that you don't have a global maximum. But it means you have to look a little bit. You have to understand the shape of your function, need to perhaps see how it behaves in the tails. Okay? So, let me take this away. Let's continue where we left off on Monday. We're looking at bivariate functions. Okay, so the beasts we are looking at look something like this. Okay, these were 2 examples of bivariate functions we talked about. That was slide 4. we ended up on slide 8. So we need to think about partial functions. Okay, and I stumbled a little bit. I looked at my slide on Monday and said, what the heck did he want to do here? So here's what I want to do. A partial function, here we have f. Now we're looking at the partial function f1. What does that mean? That means we're looking at the function, which really is a bivariate function. It has 2 arguments, but for argument's sake, we are only looking how x1 varies, and we are setting x2 to a constant. Okay? So here 2x2 appears twice here, this term here and this entire term. Here we have x2. So these 2 terms will now treat as a constant. Okay? You could think about calling this one here b and calling this entire term here c, just to get rid of this pesky x2 notation for the time being, because for the time being x2 isn't a variable. We treat it as a constant. Okay? And then, that's where I stumbled on Monday, and if you do this, you get this function. Okay? We just replace these 2 things. But now, of course, x2 could take all sorts of different values. Okay, so we need to think about a particular fixed value for x2. So we fix x2 and think about what is left over as a function of x1. So if you do this, for instance, if we set x2 to -4, so if you plug -4 in here for x2, so that is x2 here, what you get is 2x1 squared plus x1 times -4, so we'll just write -4x1. And we plug -4 in here, that's 16. 2 times 16 is plus 32. Okay, so the partial function of this particular bivariate function with respect to x1 fixed at x2 equals -4 is this one. Let's jump to the next slide. What do we mean with this? I'll come back to this slide. Okay, here's our function. This function here is plotted. Okay, it looks like a nice dish, right? You have a fruit bowl, or you're perhaps chasing radio waves in the sky. Who has been to Jodrell Bank? One, I see. Okay, are you local from here? Yeah, okay, so you would have been. Jodrell Bank is an observatory, a radio telescope, a huge radio telescope. It's part of the university. It's not far from here. It's a super nice bike trip. I think there are buses there as well, but it's perhaps not so easy to get to. But if you have the chance, go there. It's an amazing piece of science, a huge radio dish, and there's a really nice little exhibition. Anyway, just as an aside. And that's what it looks like a little bit, right? So what do we mean with a partial function? So what we're going to do is we said we fix x2 to -4. So here we have our function. We fix x2 to -4, and what you then get is you're basically cutting out a slice, a very thin slice of this function at x2 is equal to -4. Okay, and what you're left with is this sort of black line, and now we are only thinking of how that varies with x1. Okay, so we've basically reduced this to a 2-dimensional space. And what sort of shape does that have? A bit like a quadratic function, right? Okay, and this is exactly what you see here. Okay, this is that function which you're seeing here. And then, of course, you could use different values for x2. So we'd have 2x1. If we set it to -2, we get -2x1 plus 8. If we set it to 0, we just get 2x1 squared. And you could, of course, use many different functions. So when you could do that, you could imagine, remember, we're talking about bivariate functions representing multivariate functions. All the techniques we'll now learn about bivariate functions sort of generalize to larger spaces, okay? So you could have an x or that x could be a lot of elements, could be up to n arguments. Okay, and then the partial function f1 would be the function where we leave x1 as a variable, but fix all other variables. Okay, we are always leaving one variable as a variable, and we fix everything else. So here, for instance, if we fix x2 equal to 0, then we get this particular partial function. Okay, so why is that important? So that's super important because what we now need are what we call partial derivatives. So, okay, let's firstly use some notation here. There's some new notation which you may not have seen yet. This little funny round delta. Okay, it's like a delta, a Greek delta. Remember when we had a univariate function, we calculated the derivative, we would sometimes say df dx, right? Okay. That was our notation in a univariate function. Now when we have multivariate functions, we have to use different notations. So we don't use the d anymore, we use that Greek delta. Is it really, is a Greek person here? Am I slaughtering? Is that a delta? No. A delta looks different, right? Delta looks like this. Is that a Greek letter? Theta. Okay, sorry, totally wrong. Theta. I'm glad you were here, okay? Anyway, we call it del f over del x1, okay? So, a different notation, it's really different notation, we can also call it like this. F prime, prime for first derivative as before, with respect to x1. Okay? This is the same thing, just two different forms of notation. And basically what we are saying is, let's find the derivative of our function with respect to x1, but holding x2 constant. Okay, so in our mind we'll be doing exactly the same trick as here for the partial function. We are setting x2 to just some constant value and ignore it when we calculate the derivatives. Okay? And that is brilliant because that means that to find a partial derivative, we use exactly the same techniques you have used so far. Because when you calculate a partial derivative, you're only, even if you have 20 variables in your function, you're only treating one of them as a variable at a time, and everything else is just a constant. That means all the techniques you've used so far to find derivatives apply without a change. The only change is in your head that you have to recognize, okay, if I find a derivative with respect to x1, everything else, even if it's called x, is a constant. x2, x3, x4, everything else is a constant. So let's see, and then the same with respect to x2. So let's calculate an example here. So here we have a function, and let's find the first derivative with respect to x1. So this guy and this entire term is now a constant because we are finding the derivative with respect to x1. So how do we do that? Nothing changed here, so that's negative 2x1 plus, so here we have x1 times x2. Perhaps in your mind, think quickly that x2 could be called c for a constant. So if it said plus x1 times c, what would be the derivative with respect to x1? c. Okay, so in your mind write c, but now we remember, hang on, c was really x2. And what about this term? 0. Good. Okay, so let's find the derivative with respect to x2. So now all these x1 terms are constant. So that is a 0. There's no x2 in here. Here, that's a constant x2, so this is just x1. And then plus 4 times x2. Okay? So we are really using exactly the same techniques we've used so far. It's just a little step you need first in your head. Okay. So how do we interpret this first derivative? Let's look quickly back at these partial functions, and that's why we looked at these partial functions. Let's look at this one because it's not so at the margin. You see this function here? That was a partial function, and that function has a slope, right? As we change x1. That slope to that partial function is a partial derivative. And you can see it changes as x1 changes, right? But was anything special about this partial function? We could have calculated an infinite number of partial functions. We have another one here, right? So the slope to this function clearly depends on x1, but it also depends on the x2 value. Because if instead of x2 equals 0, we chose x2 equals -4, then we may have a different slope. Okay? So partial derivatives depend on both x1 and x2, potentially, but they are only the partial derivative with respect to one of these variables. So we are always looking for a slope in the x1 direction. Okay? And you can immediately realize if we are looking at a partial derivative with respect to x2, then we are in our mind fixing x1 at a particular value. Let's say this value, and then we are looking at the slope of this partial function in the x2 direction. Okay? So, what the partial derivatives give you are basically the slopes of a function in a particular direction. Okay? Either into the x1 direction or the x2 direction. But since our function is some sort of weird construct, we can calculate that slope at any point. At any x1, x2 combination, we can calculate a slope in the x1 direction and a slope in the x2 direction. Okay? And that's what we do with this. So, okay, we looked at not the contour maps. Actually, I won't do that here, but we looked at these to illustrate what the partial derivatives are. So here, and we are looking at the graph on the next page, let's pick out a particular point where x1 and x2 are equal to 2. If you plug that into the function, you will get a value of 8. Okay, so we are talking about that point here. Okay, it has a height of 8 and x1 and x2 values of 2. Okay, that point. So we are now asking if we are calculating the partial derivatives as we've calculated them above, they are functions of x1 and x2. And if we want to find out the slope in the x1 direction here, so it'll be that slope, or the slope in the x2 direction, it'll be that slope, all we have to do is we have to plug these values into our formula. Okay, so what we get is that the partial derivative at p with respect to x1 is -2. So let's see, x1. As we increase x1, what happens to the function? Is the function value becoming larger or smaller? It's not so, remember this is two-dimensional representation of a three-dimensional object. For some that's easy to imagine, for others that's perhaps not so easy to imagine. But can you see, does the function go up or down as we move from here along? It goes down, okay? It goes down, -2. What if we increase the x2 value? So we go in this direction, does it go up or down? Up. So we expect a positive partial derivative. Okay? And that's what we have here. Does that all make sense? Okay? So really the important thing you need to realize is you're not learning any new techniques here. Absolutely no new technique. It is just application of your old derivative rules just in a new context. So, what we've done with first order partial derivatives, so the first derivative, where there is a first derivative, there's a second derivative, okay? One of the basic lessons of life, hopefully not. So here we go. In the univariate case, we had, it's very exciting I know, right? Okay, we had fx, f prime of x, and f double prime of x in the univariate case. One function, one derivative, one second derivative. So now we have in the bivariate case, oh actually, before I do that, I said everything we talk about here generalizes to higher dimensional cases. What if our function had 5 arguments? 5 input variables. How many partial derivatives could I calculate? 5. Okay? That seems straightforward enough. Wait until you think about the second order partial derivatives. Okay? So here we had 1, 1, 1. That was pretty easy. Now in the bivariate case we had one function, 2 partial derivatives. How many first order partial derivatives? How many second order partial derivatives do we get? 4. Because we can take this first order partial derivative and find the second order partial derivative with respect to x1 and with respect to x2. Okay, because that is a function of x1 and x2. And we can take the second order partial derivative, the first order partial derivative with respect to x2, and we can find the partial derivative of that with respect to x1 and to x2. So 4. Okay, so here we have them, okay, and this is again just a bit of notation you need to get familiar with. Either f double prime 1, 1, so second order partial derivative, we're taking f prime 1 and find another partial derivative with respect to 1. Okay? We could also say that we take the first order partial derivative. That was the notation for the first order partial derivative. You can check 3 slides before. And then take the partial derivative of that with respect to x1. Okay? Or we can just say this was again the first order partial derivative, and we take the partial derivative of that whole thing with respect to x1. Or we say we have the second order partial derivative with respect to x1 squared, which means nothing else as with respect to x1 times with respect to x1. All these 4 things mean the same thing. And in fact, in some textbooks you will see this one, f11. Okay, they use that just to indicate derivatives. Okay, but I'll try to avoid that. Then we have the second order partial derivative with respect to x2, the first order partial derivative with respect to x2, so that's the second order partial derivative where we take the first order partial derivative with respect to x1 and take the partial derivative with respect to x2. And then vice versa, we'll take the first order partial derivative with respect to x2 and then take a partial derivative with respect to x1. Now, there's one nice thing about this. We said we had 4. Turns out these 2 are almost always the same. Okay? In the cases where they are not, we don't bother about. Okay? So effectively you get 3. So of course always a nice test. You can calculate both and see that you get the right result, as you should. We sometimes call these also the cross partial derivatives. So let's do an example, okay? Because that, I totally understand this is just a lot of mumbo jumbo notation, but you just need to know it so you know what you read. Here's an example. Here we have a function. Here's the first order partial derivative. We set all the x2 terms to constant, so we have 10 times 1 over x1, okay, minus 2 times, let me see, am I right? Mine, that comes from here. Oh yeah, okay. So 10 over x1, then we have another x1 term here, so that's negative 2 times x1, that's this one, and then we have an x1 term here, and the x2 is just a constant. This will be 6 over x2 minus x1 minus 2x2. Okay, check that you can replicate this. So then the second order partial derivative, f11, means we take this guy here and find the derivative with respect to x1 again. That was the second x1. So we are treating all the x2 terms as a constant. So this here will be a constant. 10 over x1, that's the same as 10 times x1 to the negative 1. So we get negative, here, we get negative 10 times x2 to the negative 2. That's the same as negative 10 x2 to the over x1 to the 2. And we get a minus 2 here. Okay, minus 2. What about this? So we are taking this result here, and we are finding the second order partial derivative with respect to x2. And here we get, let me do it in 2 steps. So we get negative 6 times x2 to the negative 2 and negative 2. Okay, and then we can take the negative out, 6 over x2 squared minus plus 2. Okay? So then, the cross partial derivative, we can start either way. Let's take f1, as we said here, and then take the partial derivative with respect to x2. The only x2 term is here, so that partial derivative is negative 1. And we can also try it from here. Okay, so we start with f2 and then calculate the partial derivative with respect to x1. The only x1 term in here is this one, and the partial derivative of that's negative 1 again. Okay, phew, we've got it right. Okay. So, I hope you again realize the actual techniques is just standard derivative finding. You just need to know what to keep constant at what point in time. So, a bit more notation and vocabulary. So these guys here, it's okay, I know. Late on a Friday, exciting new stuff. Okay. In here, can you please, everyone? Thank you. So in here, this is the sort of stuff we just calculated. First order partial derivative with respect to x1. First order partial derivative with respect to x2. Okay? It's 2 terms. Now, so we are still working in a bivariate function, 2 arguments. Sometimes we talk about a Jacobian or Jacobian vector. What does that mean? And sometimes that's labeled like this, a big D and then f of x. That means that basically we're just having we are sort of collecting two partial derivatives in what we call a vector. On the next slide, I'll tell you about matrices. Now, formally, I'll only talk about vectors and matrices next week, and we'll talk about some algebra we'll do with this, okay? But it's worthwhile doing this here. F1, F2. What does that mean? So now I'm using some advanced teaching techniques, so let's see whether that works. Okay. What do I mean when I say this is a vector? A vector or matrix is nothing else but a container like this, okay? Like an egg. This used to be a six egg container, so now it's only a 2 egg container because we only need two things, right? We have two partial derivatives. So all this is basically saying, let's see whether my trick works. Yeah, okay. We're having it like this. Okay. We're just having a container, and we have one first order partial derivative and another first order partial derivative, and they have some labels. Okay. And sometimes we call something a gradient vector. And a gradient vector is nothing else but the same thing, just turned around. Okay? So this is what we call a row vector, the Jacobian. This is what we call a column vector. Okay? But it still has exactly the same stuff. Okay? So at this level, vectors and matrices, or vectors in this case, is really nothing else but a container which contains a number of things. And that may be a formula, a value, okay? So in the gradient vector, so we call it the gradient vector, then we always also sometimes call this with this inverse delta. Does that have a Greek name as well? Or is that just an inverted delta? Inverted delta, okay. And we just put that on its head, okay? So, this was a 3 by 2 egg container. What am I going to do with this? I'm going to make a Hessian matrix out of this. Okay, let me see what I mean. So, then there's something which we call the Hessian matrix. So we are still working in this. Oh, I should say, if we had 5 arguments, if we had 5 input variables, how many places would I need in my container? I would need 5, right? 1, 2, 3, 4, 5. Okay. So, what's the Hessian matrix? We're working in the same environment, our bivariate function. Remember what these terms were? These were the second order partial derivatives. And we said we had 4 of them, right? So the Hessian matrix is nothing else but, which way? A container. Okay? A container for our second order partial derivatives, in this case 4. F11, F12, F22, F21. Okay? Nothing else but. So next week we'll do more with a container. We thought so. So to speak, we're going to smash up the eggs. Okay? But I'm not going to illustrate that. But this is nothing else, the Hessian matrix, but just a container which contains these 4 things. Each of these guys is a formula, right? Each of these guys is a formula where each individual value depends on the x1 and the x2 value. Okay, whatever value we choose for the x1, x2 pair, then we can plug it in and get a number. But until we do that, each of these is a formula. So each of these is a formula, and once we fix the x1 and x2 values, they will turn into a value. Okay. So why is this important? All I have here on this slide is I put all of the calculations, all of the formula we've calculated, the first order partial derivatives, I now put them into that gradient vector, and all the formula for the second order partial derivatives, I put them into here, into the Hessian matrix. And I drew out the minus. Okay, it's like a factor. So it's minus that, minus that, minus that, minus that. Remember the cross order partial derivatives were minus 1, so minus 1, minus 1. So why is this important? Well, because of the following. Remember in the univariate case, what did we need to do to find a maximum? Or an optimum in general, okay? First, we had to find a stationarity point. So we had to find where f prime of x is equal to 0, okay? And then we had to identify the sign of the second derivative at that, let me put a little 0 here. We had to find the sign of the second derivative at that point. And that would tell us which way the function was bending and whether we had a local minimum or maximum. So in principle, we need to do exactly the same when we are dealing with a bivariate function. So what's that mean? We have to find a stationarity point in a bivariate function, or more generally in a even higher dimensional function. We need to find that point where the gradient vector is equal to 0. Now what's that mean? Here's our gradient vector. It has two elements. So we need to find that value where both these elements, that one's equal to 0 and that one's equal to 0. How many equations? 2. How many variables? 2. Can you solve it? Yes. Good. That was the right answer, by the way. Okay? So yes, we need to two-equation system, you need to solve it for x1 and x2. How many solutions could you have? A lot. Okay? If you have linear equations, you can have... Think about it. Okay? But in general, so it's just a general point. Okay? So, that means we can find the stationarity points. All is still honky-dory. But then we need to do the equivalent of this. We need to find the sign of the second derivative. So we need to find the sign of the Hessian matrix. We need to find the sign of this guy. And now we are stuck. Okay, now we are stuck. Because we have 4 elements in here. And it's perfectly possible that 2 of them are positive and 2 are negative. So what is then the sign of H? Okay? We don't know. And perhaps to illustrate why this is now more complicated and why we need the techniques I'm going to introduce you to next week, or starting with next week. It's possibly going to take 2 weeks. You can perhaps see when we look at this function here. So we're going back to slide 13. Okay. This function at that point, is that concave or convex? Convex? Anyone have a different view? So we have one view here that this function at this point is convex. And look, if you look this direction, right, it looks convex. But what if you look at this direction? It looks concave. Okay? So the question of whether something is convex or concave becomes much more complicated. Okay? And that's why we need new techniques. And we will show you a technique which tells you something about there is... Please, I know we're only having a few more minutes left. Okay? But for these, please concentrate. there is actually something like a sign to such a matrix. There is something, okay, and we'll tell you. It's called whether a matrix is positive definite or negative definite. And we will find matrices which are positive definite. That's like saying that this matrix is positive. And that will then say that the function at this point is convex. And or we could find that that function is positive definite. That Hessian matrix is positive definite at that point. That would then indicate that the function at a particular point is concave. But there will be many situations like the one we saw in the previous picture where that Hessian is neither positive definite nor negative definite. So neither concave nor convex. Okay? But we need to do a little bit of legwork. And while so far I told you that this Hessian matrix is nothing else but just a container, in the next couple of weeks we'll have to learn how to calculate with egg containers or matrices, okay? So, give me 1 minute, guys, okay? Listen. For these slides, I will record a video. By the way, I uploaded the cost function video now. It's in the week 3. I will record a video. This is especially important for those who are doing analysis courses, okay? Because you're talking about stuff like that already, but I'll record a video. Have a great weekend. Anyone need eggs? Thanks.
I know this is cheeky, but is there any chance I could get your paper of lecture 4 slide 20?
Sorry, what lecture?
Lecture 4 slide 20. I was wondering what you were going to do with it. Like you had them at the start of the lecture.